Hello, everybody. I think it's time to start. Sorry for being late. So yeah, we're so happy to have all of you here. Today with us is Dr. Professor now, Ramona. She did her PhD thesis in category theory, and then she decided to do something useful and did her postdoc here in the QIT group in quantum key distribution. And now she has a professorship in Germany, in Siegen, also doing quantum key distribution or quantum cryptography. And yeah, today she's going to tell us something about the physics of randomness. And with that, the microphone is yours.
Thank you. Yeah, I'm very happy to be here to talk about randomness. It's one of my favorite topics because everybody kind of has an intuition of what randomness is. But when we use it in a scientific context, we somehow need a more mathematically precise definition. And in this talk, I want to explain to you a bit the concept of randomness and also try to show you that it's not as trivial as it may sound from the beginning what it is. So the talk is rather conceptual and not so technical. So there will barely be any formulas, but we'll talk a lot about concepts and definitions and how to justify certain definitions. And maybe this kind of work or this kind of thinking is a bit, you're not so used to this because it's rarely done in lectures. So if you have any questions, I encourage you to just ask questions during the talks. That helps in understanding everything better. And we'll go through, you see a lot of examples of scenarios where randomness plays a role. And then I will use these examples to show you where your intuition might go wrong or different aspects of randomness. So you'll see a lot of pictures, not so many formulas. Okay, but let me first say something about why I'm even asking this question, why I'm so interested in finding a precise definition of randomness. Is that something that should interest us? And the thing is, randomness is everywhere in our daily lives, when you play board games, when you go to a casino and gamble, when you're into cryptocurrency maybe, or when you're doing science and you want to do a bell test, you also need randomness to choose measurement settings. And actually, in many experiments, randomness plays a role in when you decide what exactly you do in the experiment or how you choose certain things. So it really is something that appears in our everyday life and also in scientific context. Okay, can I hide this? How do I hide this?
That was just me.
Yeah, thank you. Do you know how to hide this? It annoys me.
It's there, I think.
Where? Is it?
And then unfixierte Meeting-Controller ist der Ausblenden.
Ah, thank you. Perfect. That's better. Okay, so randomness appears in many contexts. In particular, it appears in cryptography. And here, it really plays a crucial role. Here, you don't just need a somewhat understanding of what randomness might be, but you need a scientific definition so that you can ensure nothing goes wrong. There's been this example, it's from 2012, where people analyze cryptographic keys that are used on the internet. You may know that RSA is one of the most used encryption algorithms that we use for internet traffic to encrypt messages and everything. And it needs some cryptographic seed. So we start with randomly choosing a number. And the thing is that people have used this, and part of the RSA algorithm is that there's a public key. And the idea is from the public key, you cannot get the private messages. And people have analyzed all the public keys that are on the internet, that's a massive data set, and checked whether from these public keys they can actually get the secrets for some reason. And they saw that many or a substantial amount of these public keys have not been generated with sufficiently good randomness. But the random number generator was not good, so sometimes it would put out the same number. That a key has been generated with two keys have been generated based on the same number. And then if you have those two keys, then you can actually get all the secrets that should have been encrypted. So they concluded that RSA can fail catastrophically when used with malfunctioning random number generators. So here, the randomness you use is really a crucial ingredient in the security of your whole encryption scheme. So it's not just that I want to find a definition of randomness because I'm interested and that's my hobby, but it's really crucial to guarantee that cryptography works properly. Okay, but yes, let's come to the question, what actually is randomness? And here I now have a couple of questions for you. So let's say I ask you, can you explain the concept of randomness to me? Who of you would say they could explain the concept of randomness to me? Like an intuition behind it. I will not ask you to do it now, so you're safe if you raise your hand. Do you think you could explain the concept of randomness? Yeah, okay. I see some people who think they might be able to say something about it. If I ask you now, could you give a mathematical definition of randomness? Who would say yes to that? Could you like write it down, a formula or something? This is more difficult, right? Okay, now I have a third question for you. You're probably aware of that there are like random number generators and there's a huge market of quantum random number generators. Do you think there's a fundamental difference between classical and quantum random number generators? Who would say there's a fundamental difference between the two? Okay, yeah, those are many people. Okay, cool. Okay, so now let's find a definition of randomness. Let's see how that goes. We'll go through a couple of examples that like give us some direction on what we actually want from this definition. Okay, so I'll show you some examples and you should think about like, would you say this is random, what I'm showing you? So the first example is just like you roll dice. And like the question is the outcome of the roll of a dice random? Who would say the outcome of that is random? Okay, divided opinions. Okay, then we have the weather forecast. Let's say, I mean, the weather forecast, it depends a bit on like for which time I'm trying to predict the weather. So would you say the weather forecast for tomorrow is random? No. Would you say the weather forecast for in a year from now is random? Or let's say it's not entirely deterministic, maybe. Yeah, okay, that's more random. Okay, now some example from that you could build in a lab. Let's say we have a photon source. That's in the description, yeah. Okay, let's say we have a like perfect single photon source that produces photons that are diagonally polarized. Then they get to a beam splitter, which distinguishes between horizontal and vertical polarization. And it sends the photon to the corresponding detector for this. And then we have perfect single photon detectors. So in that case, if we're in this like perfect world, no noise, everything is exactly as I wrote it down here, then only one detector will click for each photon that is generated. So you can just take the clicks of the detectors as zeros and ones, and this is your random number generator. Would you say that this generates true randomness? Who would say that? Okay, that's quite convincing. Now I have the exact same setting, but now I take this produced randomness and I store it on a USB stick and I retrieve it later. Is this still random? Who would say this is still the outcome, like what I retrieve from the USB stick in the end is still random? Okay, you seem confused. Yeah, you'll see the difference later. But yeah, it's a bit of a journey until we get there. Okay, but I mean, what this clearly shows that it's not really easy to decide whether something is random or not. It seems to be a bit like, it's a bit difficult because, well, we don't have a definition yet, right? So what we will do is we will develop a definition and then we come back to these examples and test our definition against the examples. Okay, so how do we define randomness? What does the definition have to deliver for us to be satisfied with it? Well, there are two ways you can start to answer this question. One possibility is you look at the outcome and you base your definition of randomness on the outcome that is produced from the random number generator. And the other possibility is that you certify the process that produces the definition. And these are two different approaches that you can do, and both of them are pursued. And I would say both of them are probably justified in different contexts. And I will tell you a bit more about these two ways of doing it, and also why I think this is the better one. Okay, let's start with the outcome-based one. So one very famous one is the Kolmogorov complexity, which looks at the string that is produced, and it says the complexity of it is the length of the smallest computer program that produces the bit string as an output. And if your bit string is perfectly random, then the smallest computer program should be as long as the bit string itself. It should be just like print bit string something. But if the bit string contains patterns or something, then you can write a shorter computer program. So if you have a bit string that is just 100 zeros, then your computer program just like says print the 0 100 times. That's certainly shorter, probably. So this seems to capture the randomness of the outcome kind of like quite well. The problem is, sadly, this is uncomputable. So there are proofs that in general the Kolmogorov complexity cannot be computed. That's a bit sad. So instead, what is often done are these statistical tests. For example, NIST, the National Institutes of Standard and Technology in the US, they have like, on their website, they give you a test suite where you can put your random bit string in and it tells you how random it is. Like it's a couple of tests and the bit string might fail or pass certain tests that tell you something about how many patterns or what kind of patterns the bit string contains. Okay, so this tells you something about patterns in the outcome bit string. What this kind of test couldn't distinguish is these two scenarios, where I store it on a USB stick or not. This is not distinguishable, so you'd be happy with that. Okay, so these are two examples of how you could talk about the randomness of the outcome bit string. And then we have process-based definitions, which would be probability theoretical definitions. So these definitions tell you something about the probability that you can predict the outcome. So if you intuitively think that randomness means that something is unpredictable, then you can say something that the process produces something that could not have been predicted. Okay, so these are the two possibilities. And then, yeah, the question is, which one do we need? Which one are we interested in? And here I want to give you an example. Yes, exactly. What I want to emphasize is which definition you need depends on the application where you want to use your randomness for. Different applications have different needs for randomness. And I want to show you one application that hints towards one of the two possibilities. And it's from the 2011 Swiss federal election. Because in Ticino, there was a draw between two candidates. So Marco Romano and Monica Duca-Wittmer, they both received almost 24,000 votes, but the exact same number of votes. And then the law says, in that case, you have to randomly select the winner. Okay, now, like, they had to randomly select the winner. So what they first did was they used a random bit that had been pre-generated on some computer without any one of the candidates or the public being present. And this bit said, Monica Duca-Wittmer wins. So like then it was announced that she won according to this process. And Marco Romano, he challenged this. He said, this is not random, or this is not certifiably random. It was just produced somewhere without the public on a computer, even like before, like it was not, you were not able to certify that this was actually a fairly random process. So he challenged this. And then the Bundesgericht in Switzerland said, okay, we define how this random bit has to be generated. So it has to be generated by, so this is from the words that the Bundesgericht said, but it basically says it has to be generated like a person who's not a member of the party of the two, has to draw a lot that then says who's the winner, and has to be public. So everybody is able to watch, in particular the two candidates, and like the public can see how this randomness is generated. So here it's important that the public can watch the process of randomness generation. And here we are in the setting where basically we need a random number generator and we need just a single bit. So we need just a 0 or 1. And if you now want to certify this random number generator that just produces a single outcome, well, your outcome-based definitions are a bit useless, because the complexity of a computer program that outputs a 0, well, it's at least 1 bit. So it's at least as long as the output string. And also, I cannot do a statistical test on a single bit. So yeah, outcome-based definitions are a bit useless. And here you definitely need a process-based definition, a definition that says, okay, this process produces a random outcome. So this shows that, like, for these kind of applications, you can only use a process-based definition. Okay, then let's find a process-based definition. Okay, so the intuition that we use is that randomness means unpredictable. So if I say this single bit that was output, I want it to be unpredictable by anyone else. Okay. Okay, the question is now, yeah, how do we define this randomness? And here I want to demonstrate something. Okay, let's say we have a perfect unbiased coin. I have one. This has actually been sponsored by Professor Renner. I met him just before the talk, and I said I needed a coin. So, thank you. Okay, let's assume this is a perfect unbiased coin. So when I flip it with probability 1/2, it shows heads, and with probability 1/2, it shows tails. Okay. Then one interpretation you could give for this probability distribution is that an agent who has to bet money on the outcome would bet the same amount of money on heads and tails. The agent wouldn't be biased towards one outcome. Okay. Question is this actually random? Will it fulfill all the properties I want from a definition from randomness? Okay, now I need 3 people to help me. Okay, Carla, you'll be my first person. No, I will flip the coin. I practiced yesterday evening. I'm not sure how it goes. You just need to say yes or no. Okay, assume we make an experiment. Okay, assume I give you 1 franc. And now you can either just keep the franc, and then you have 1 franc more, or you can bet it on, let's say, heads. And if the coin shows heads, then you get 5 francs back. So you have the decision between having 1 franc deterministically, or maybe like 5 francs. Would you bet this 1 franc?
Yes.
Okay. Okay. So now I'll flip the coin. That's pretty good. Okay. You're my second person. Okay. Now I flip the coin. I offer you the same thing as I give you 1 franc, and you can bet it on heads or not. Would you say yes? Would you bet it?
Yes.
Okay. And now I take a third person, you. Okay, I show you what it shows. So they bet on heads. I show you this. Would you also bet on heads? I wonder why. Yeah, okay, so it shows tails. And what I want to demonstrate with this little experiment is that the probability distribution, it's not a property of the coin. It's a property of your knowledge about the outcome. They both didn't have any knowledge on it. And like the difference between them was, in the meantime, I flipped the coin. So the coin did have a definite outcome here, but you didn't know about it. So on your knowledge, nothing changed. It was the same for you too. But for you, you saw the outcome. So for you, the probability distribution changed. And you would not have bet on heads. Okay, so what this emphasizes is that randomness is knowledge dependent. For you, it wasn't random anymore, but for you, it was completely random. And even for you, it was still random because while the outcome existed, you didn't know about it. So somehow we need to capture that this probability distribution is not an absolute thing. It's not a property of this coin, it's a property of your knowledge. So we make this explicit, and we write down probabilities as like the probability of an output given the knowledge of the agent that talks about it. And then the knowledge is agent dependent, and it's also time dependent. And I want to show you why it's time dependent with a different example, which is roulette. It's a very nice example. I've actually never played roulette myself, but I've talked about it a lot in my talks. Okay, so if we have a roulette game, then well, at some point in time, the roulette ball will be released. So the wheel spins and the roulette ball will be released, and it wobbles around and eventually sets into position at some place. And the outcome of, like, say, which number it takes, we call it R. This is our random number that we have generated with this experiment. And you would say, before the roulette ball has been released, then you could say the probability distribution for the outcome is uniform. Like let's say for us that we play roulette, we can't predict anything about it. So the probability of the outcome given our knowledge, standing in front of the roulette table, is uniform. We would bet the same amount of money on each number. And then it starts to spin in the wheel, and maybe it's slowly turning towards a certain direction. So here, the probability is evolving. So an agent in this time span would not say that the probability distribution is uniform anymore. At some point, you can pretty well like estimate where it will land. And if you have a super good like camera and computer program, I think you can at some point actually determine where it will land in the end. And of course, after it has been generated, then it's deterministic. Then one outcome has probability 1 and the rest 0. So you see the knowledge about the probability distribution, it evolves in time. It starts from a uniform one and ends up deterministically. And if we make it a bit more abstract, this idea, then you would say that you have some agent that at the point before the randomness generation process has been started, then like stuff happens in the middle. We can't say much about it, it just like evolves. And after the randomness, like at some point the randomness has been generated. So there are these 3 different points in time that you distinguish. Okay. And you could, like intuitively what you want from this point, this randomness here, is that it can't be predicted from the point before the process has been started. So as long as the ball is not rolling, you want, like from that point on, like when it's not rolling yet, then you can't predict the outcome. It's just a uniform probability distribution. And this, the knowledge, so that means if you have the space-time diagram, then everything in this, let's say here the process starts, then everything outside the future light cone, from all the space-time points here, you cannot predict the randomness here. And if we phrase this now as a definition, you can say the randomness, like R is random with respect to this space-time area if the probability distribution of R given all this knowledge here is uniform. This would be our process-based definition of randomness. We don't aim to say anything about what happens here. Like if you have this roulette example, then there's a, like players can still bet on the outcome while the ball is spinning, and at some point the croupier says nothing, like no bets anymore. But it's very hard to make precise mathematical statements about the part where everything evolves. But what we can do is make a statement about the area before the process has even started. Okay, so this will be the definition that we go with randomness. It has, it's been motivated by the example that I gave you before, that it is that our knowledge evolves in time, and that we need a process-based definition because the outcome-based ones don't always work for all applications. And what is very important here, what I want to emphasize, is that if R is random, it's not an absolute statement. It depends on how we define this knowledge. So it's always random with respect to knowledge that someone has. As you can see here, this knowledge is defined by the point in time where the randomness generation process starts, which we call the trigger event. And this will be the crucial task when we see examples to define where exactly did the randomness generation process start. So what is the trigger event of our random number generation? Okay, so let's go back to the examples that we had and see if those are random according to the definition we now have. Okay, I want to start with the last one because this is actually the easiest one. This is our random number generator based on photons that we send to a beam splitter. Now we can draw the space-time diagram with these different steps. Okay, it's very clear that after the bit has been generated, after the photon has been detected, then the probability distribution is deterministic. We know whether it is 0 or 1. Okay, so if I write down the whole thing, like I write down the quantum states and do some math, we have the photon source sends out a state in a superposition between 0 and 1. And now I want to make a short excursion about randomness in quantum physics, like in the mathematical formulation of quantum physics. So let's say I have this state written down in a superposition of 0 and 1. And now I measure in exactly this basis, in the computational basis. Then using like the standard Born rule for the probabilities, you see that the outcome 0 has a probability of 1/2 and the outcome 1 has a probability of 1/2. Okay, now instead of this state, I use a mixed state, a maximally mixed state, where I have like a classical mixture of 0 and 1. And I again use the Born rule, and I get the outcome that both outcomes appear with probability 1/2. But clearly, it's a different state. So what's the difference here? The thing is, for the example where I started with the mixed state, there exists a pure state, like an extension of the mixed state, such that if I trace out the helper system E, I get the original state. But as you can see, it's a maximally entangled state with the helper system. So if you have access to the second system, the system E, you can predict the outcome on system A with certainty by just doing the same measurement on your qubit. So clearly, in this point, like here, the outcome is unpredictable for everybody. But here, if you have access to the system E, the outcome is not unpredictable. So this is not the setting that we can use, because if we want our outcome to be unpredictable for everybody, then we can't allow there to exist extensions where someone can predict the outcome. But here we're safe, because if we have a pure state and we see that it's uniformly random, then no one can predict the outcome better than us. And this is actually a result from Professor Renner and one of his postdocs, Roger Kolbeck, from 2011. So if if you have a pure state and the Born rule predicts that the measurement outcome is uniformly random, then the outcome is actually unpredictable. This is called the completeness of quantum theory. So there exists no extension that gives us better predictable powers than quantum theory, and with this, the Born rule. Okay, and what this excursion now tells us about the example we're looking at is that if we know we have prepared the state at the beginning and we do the corresponding measurement in the computational basis, then we know that this probability distribution is random, that we can use what the Born rule tells us about the outcome probabilities. Okay, this also shows that, it shows the importance of being able to know that this is a pure state, because only when we know that we have a pure state and we make measurements on it, we know that the outcome is truly unpredictable. Otherwise, if it's a mixed state, there can always be an extension system that has information on the state. So that it's crucial that we have a pure state at the start of the randomness generation. Okay, so with this, we can say that this setup is really a true quantum random number generator. Like, this produces true randomness. If you can build this in the lab, you're safe. This is exactly what we want. This is fundamentally unpredictable for everybody. Okay, now we had this extension where I first save it on a USB stick and then retrieve it later. And if I put this into my space-time diagram, then you have just an extension up there where you save it and retrieve it later. So this is the randomness R tilde. Okay, so before, what we could prove in the setting before is that this outcome is random with respect to all the knowledge that's here in this space-time region K. That's what we can prove. So now, with this setting, what we can certainly prove is that the outcome R tilde is random with respect to this region, again, because nothing has changed. But the question is this a relevant statement? Does this help me? Is this useful randomness that I'm producing? And the answer is, well, probably not, because you could retrieve the randomness way later, like next year. And the only guarantee that you have is that it is random with respect to this knowledge. So you know it is random with respect to someone who has been there with respect to knowledge that has been generated a year before. So if you want to use it for, let's say, a lottery game or so, it's very useless, because in all of this time, people could have gotten access to the randomness. So yes, this is still random, but only with respect to something in the far past. Okay, and could we prove something stronger for this? No, because from here on, it is deterministic. So the pure state that we need to prove randomness, it exists here, but here it's certainly not a pure state anymore. So any proof that we can give is only with respect to this area. Yes, please.
Is there any intuition behind the idea that the randomness gets lost between R and R tilde, even though?
I mean, it doesn't get lost. The thing is, it's still random, but with respect to, like, you can prove that this is random with respect to knowledge in this space-time area. And the thing above is still random with respect to the same knowledge. So the randomness is still there, but it's not as useful anymore because for, like, basically all applications, you would need randomness that's random with respect to something that's closer in the past.
And how is someone that is in the, so someone that isn't in the space K, so that is in the closer future, I guess, how would they like gain X, or why would it not be random with respect to them?
The issue is that it's in principle possible for them to get this information or like to just copy it from the USB stick. What you can show is that when you're an agent here, it's fundamentally impossible for them to know the randomness. While here, it's now like nature doesn't prevent the agent anymore.
So we're not talking about the safety of the stick at all?
No, not at this point. It's about, like, is it fundamentally possible to predict it? Of course, if you could keep your USB stick safe and guarantee that no one has access to it, you're still good. But it's about, like, what is fundamentally possible, but what does nature allow us to do? Okay, so as a short intermediate summary, if we define randomness, then it's always with respect to an agent or the knowledge of an agent, and also always with respect to a trigger event. So nothing is absolutely random. It's always with respect to some point in time where we can actually say that there has been a pure state. Okay, what I haven't talked about so far is the difference between classical and quantum random number generator. The definition in principle is valid for both. It doesn't distinguish between quantum or classical. The argument I gave you with the pure state, this is of course a quantum argument. And now, the question is, I mean, if our world is fundamentally quantum, so if you agree that everything is described by quantum theory, does it even make sense to speak of classical random number generators? Or phrased differently, if I, what do I want to say? Like, can I even define something like a classical random number generator? It seems a kind of very arbitrary concept in a world that's fully quantum. So what do we even mean when we say this is a classical random number generator? Like, could you define a classical random number generator?
Maybe, I mean, I would try to wash out the quantum behavior and make something where I can predict with certainty it's like either in this state or in that state, and then just produce like a mixed state in that sense.
Mm-hmm.
Then that way I will produce like a...
And what's your argument then for that it still produces a random output? Because now I just described a deterministic thing. Yeah, okay, I mean, I'll talk about this. Actually, this is something that, so I had a meeting with Professor Renner just before this talk, and today we finalized the definition of randomness. So this is like very fresh. But now we're pretty sure that this is correct. Okay, let's again like go back to these examples and see, like if you describe the whole world as quantum, what could you say about this example? So you can you would write down the quantum state of your dice and how the quantum state evolves in time in a fully quantum description of the world. And then again, you can write down your space-time diagram and see what the different stages are. So you could argue the start of the randomness generation process would be the point where you roll the dice. That seems natural. Then stuff happens, and then the dice stop, and you get some outcome. Okay, but now the question, as I said before, it's if we want to show something mathematically, we need a pure state at some point. This is the way we can prove that something is random. And the question is, well, was the dice in a pure state here? I mean, if you just look at a pair of dice, how can you determine whether it's a pure state or not? It's probably not in a pure state. I mean, maybe you can argue at some point in the past it was a pure state, what you could probably say is that at the Big Bang, the whole world was in a pure state. I mean, you can also argue about that. But you could argue for that at the Big Bang, everything was in a pure state. But this is kind of a useless statement. So then you know the outcome is random with respect to before the Big Bang. So the question is, where can we say that the quantum system was in a pure state? Because now we're describing everything quantumly. So for it to be able to be uniformly random in the end, at some point it has to be in a pure state, and this would mark the start of the randomness generation process. And with dice, this seems very difficult. We also had the prediction of the weather. So at some point, you could say the randomness generation process, if you would use the weather forecast to produce randomness, it would start with the point where you make a prediction, and at some point the day actually has come and you can see the weather. And well, this is even more difficult. If you describe the whole weather, Earth, the clouds, everything as a quantum system, then you need to argue that at some point the weather was in a pure state. And I mean, when I asked before, there was a kind of an intuition that the weather forecast for tomorrow is probably not as random as the weather forecast for what happens in a year from now. And that, I mean, that means something like in the past, at some point, if there's more time between 2 points, then probably this thing was in a more pure state in the past. But you see that it's absolutely impossible to determine the pure state of these systems, to say when there was a pure state. While if you remember for the quantum random number generator with the photons, we could pinpoint down the exact point where the pure state has been generated, because our photon source just produced the pure state, so you could really write it down. Okay, so the proposition to distinguish between quantum and classical randomness that we make is that the time between this trigger event where you have the pure state and the time where the randomness has been produced is a measure of how good your randomness is. So what we argue for is that it doesn't really make sense to say something is a quantum or a classical random number generator if our world is fundamentally quantum. But what we want to distinguish is good and bad random number generators, like in a fundamental sense. What can we fundamentally predict well, and what can we fundamentally predict not so well? So what's the measure that is important is where's the earliest point here with respect to the outcome that where's the latest point in time where you can put the trigger event such that the outcome is still random. And then if you look at the settings, like in the quantum case, you can actually, first of all, this point in time is well defined, so you can pinpoint down this is where it started. Okay, so as I said, we're proposing that this generation time is actually a good measure of whether a random number generator is good or bad, and that it doesn't really make sense to say it's classical or quantum. And then if you look at the quantum random number generator that uses photons and measures them, then you can pinpoint down this point in time where the process started, and you know when it has been produced. In this generation time, it will be super short. Like, this is something that happens in a very short amount of time, something that's much smaller than seconds. So for a quantum, what we would say is a quantum random number generator, this generation time is super short. And you could see that this is actually what we want for applications. We want to press a button and get a random number immediately, basically. And we also want that when I press the button, this is the point in time where the process starts. So a small generation time fits exactly what we want from a good random number generator. And if you instead look at classical random number generators like a dice or the roulette or so, then first of all, this point in time is not particularly well defined, as I showed you with the dice or the weather. It's hard to pinpoint down where the process started. But usually, like, this generation time will definitely be much larger than seconds, because while you can't pinpoint the exact time when it started, you can give bounds on it. So for the roulette, this time will be at least the time between where the ball has been released and where the ball has settled in the pocket. So this is larger than seconds. And I mean, for the weather, it was, I think it's maybe weeks or a year at least. And also for the dice, it would be like, maybe from the point where the dice like leaves my hand and stops on the table, which is also larger than seconds. So classical, what we would call a classical random number generator, something that needs, that is at least several seconds. And this gives you a measure to determine how good a random number generator is. And also, like, it's clear that we want a generation time that's very short for most applications. And here, I mean, you can't really calculate the generation time, you can only give bounds on it. But it shows that it's a good measure to distinguish what we intuitively understand as quantum or classical randomness. Okay, and this, yeah, this is very fresh research that has not been written down anywhere yet, except in like notes on an iPad. Yes, please.
If you give for the roulette bound that the generation time is at least the time between releasing the ball and the ball settling, what do you mean with settling? Or I mean assuming that every bounce that the ball makes has some small quantum uncertainty, then it is not clear to me that the generation time has to be this long. It could be that like 20 bounces is enough to completely scramble the result instead of all the bounces from the beginning to the end.
Well, okay, I mean, what you need for this point in time is that the ball or the roulette game is in a pure state. And while this is super hard to determine, I'm pretty sure that when I release the ball, that's not a pure state anymore, because I think you can, with the proper equipment and computational power, you can determine where it ends up once it's rolling.
I can do this before it even started to, or no.
I mean, because also me releasing the ball is a deterministic thing.
But then the release time of the ball is itself a random process. If it isn't, I could extend my predictive powers.
I mean, yeah, you make good points. And I think the most important takeaway from that is that this is, you can't calculate this for like classical random number generators. It's not, these points in time, it's not well defined. But for this setting, everything is super well defined. So like so if you want to say something about the quality of your random number generator, then clearly if you have such a setup, you can sell this very well to people. Like if a company would buy this, if you tell them this is a good random number generator, but they won't necessarily buy this because you can't make any quantitative statements about it. And that's the main point of this definition. So we don't aim to actually calculate this for classical random number generators, but now it's like you actually have a mathematical quantity that shows quantum random number generators are better. Yes?
I don't recall exactly how pseudo-random number generators work in an electrical circuit, but they somehow, at least what I remember is they are way faster than seconds. So how do, and is it that obvious that the quantum random number generators are that much faster than these?
I think the issue with the pseudo-random number generators is that this point where like the process starts, the quantum system is not in a pure state. So according to the definition that we have, the generation time would be much longer. So that's how they differ from, I mean, it's clear that various kinds of random number generators are useful for different purposes. Okay. But this is, so what we aim for is, like we're asking the question, what can we actually prove mathematically? And then, of course, I can use a pseudo-random number generator for various applications, but if I want to talk about like fundamental randomness in nature, then this doesn't, this gives you a generation time that's longer than seconds. Yeah.
Also, wouldn't this somehow mean that if I just make if I make this whole setup large and let the photos travel for a long time, then it gets worse?
Yeah, it does. That's true. I mean, you can use quantum setups to build a bad random number generator in this setting. That is, yeah, that's actually an interesting point because I would still say it's random, but yeah, I mean, why would you do it? But yeah, and then yeah, this generation time will be large and your trigger event will be somewhere very much in the past. But yeah, you can. Yes.
Yes, so my question would be, if I understand correctly here, we are only taking into account for the sort of how good the randomness is, the trigger event itself, and the time between the trigger event and this orange point from which on this is deterministic. So why is it independent of the process itself between the two? Because, for example, intuitively, when we are considering, for example, this better between a day and a year, one would think that it is more random, as you mentioned. And I understand it would not be very useful if we had to wait for a year to generate something random. But is there a more fundamental reason for this? Is this, for example, because we are considering everything quantum mechanically, so we just say that it evolves in a deterministic way according to the Schrödinger equation, or some other reason?
I mean, the thing is, the question is always, what can we actually prove? And as I said, like, this is something where, like, if there's a pure state here, I can prove that the outcome is random. Of course, like, in the time where it evolves in this process, it's not entirely deterministic either. Like, it still contains some randomness, but I can't really make a mathematical statement about it, or at least not very easily. Maybe I could, like, model the process, as I said, with a Schrödinger equation or something, and then still say something about how much randomness it contains, but it gets much more difficult and it depends on how you model certain things. So this is really, like, this is something that I can actually mathematically prove, that if there's a pure state at this point, then the outcome will be random. And everything afterwards is much more complicated and, yeah, not as mathematically rigorous. And, yes?
Just one quick question regarding the goodness of randomness. You said that randomness is good if this time is very short, but does that mean in any sort of application we want to use the random number, say, that we generated almost instantaneously, and does that also mean that the randomness gets worse the longer we wait with using whatever we generated?
So the motivation for this is that it's like the randomness that is produced, it's always only random with respect to this area in space-time. So if it takes a lot of time, then my guarantees are weaker. And in most applications, I want to have it like in cryptography, I need it to be random with respect to, like, anything that I want to keep my secrets from. And usually, if it's a long time, then I don't have any guarantee for this in-between time where the process was. So it's, I mean, there are probably applications where that's fine, but in most applications, it's useful to have this very short, so you have a huge amount of space-time where the randomness is unpredictable. Yes?
I was wondering about the trigger point, or like this trigger, if there could be any scenarios where it's maybe well-defined in space-time, but maybe there could be two triggers, or there's like some weird stuff going on that it's not well-defined, like in that regard.
Yes, that is that's a very interesting point, because as I said, like, now we want to model everything quantum mechanically. And then there's the question of where, if information is actually localized in a single point in space-time, if I model everything quantum mechanically. And this is actually highly non-trivial. And this is actually what Carla and me are investigating. That's part of her PhD project, to see, like, if I'm very rigorous and, like, model everything quantum mechanically, then there are cases where information is not localized in a single point in space-time, but it's like a different location, so it's just not well defined where it is. And in those settings, what can we still say about, like, cryptography, randomness? But yeah, it's a very non-trivial question. Yeah.
Regarding the quantum random number generator, couldn't I, like, extend the trigger event or push it just shortly before the two detectors, or one of the two detectors would click? Because I guess the photons, even they will still like, travel in superposition.
You mean you don't want to put it here at the point of generation of the quantum state, but just a bit later?
Yeah, like just shortly before like one of the detectors will detect, because I guess the collapse really only happens when one of the detectors clicks.
It's again the point of what I can prove, actually. And what you can prove is that at the point of generation, the outcome is unpredictable. But you can't directly prove that, because here, like, the quantum state evolves when it travels through the setup, and then you can't make the mathematical proof in the same way as before. Then it depends on, like, what you can assume that your quantum state doesn't change when it travels through the fiber or something. But you can't, like, put it on the same mathematical rigor as before. Because it's the proof that, like, if I produce a pure quantum state here, that the outcome is random, this is very fundamental. It just says, if it were differently, then you could violate non-singleting. So it's based on very fundamental physical principles. But as soon as you try to put the trigger event further, then you, like, have to model the time between the generation and the point you put your trigger event. So it's not as mathematically rigorous. So it then starts to depend on how you model certain things. So it gets more difficult. Yes?
The well-definedness here is also dependent on the fact that the state that so basically the point of TT I've defined as the point where I have a pure state.
Yes.
But I think one of the examples from before showed that I can never be 100% sure that I have a pure state, no? Because I can have the same statistics, but they're not pure states.
Yes, so, like, in some sense, it's an assumption that you make, or let's say from when I have either the pure state or this maximally mixed state. If I just measure, like, say I have a source that can produce either, and I just measure and try to find out which is it, then you can't do it. But for example, in a Bell test, I can, like, if I do a Bell test, then I can, from the statistics, get more, like, stronger knowledge about the quantum state. So I need to somehow ensure or assume that it is a pure state. Yes?
When we define here the generation time, we're taking the minimum between, this TT and TR, such that this probability is still uniform. But what does it mean that this probability is non-uniform? Like, could the generation time be too small? Or what does it exactly mean?
So the generation, this trigger event, it defines the space-time region with respect to which I want this probability to be uniform. And if I put the trigger event too far up, then too much is included in this region, such that I cannot prove anymore that the probability distribution is uniform. That's always the point. It's the time such that I can still prove that this probability distribution is uniform. Yes?
So one last question about this trigger event. If we, like in the classical case, you mentioned a couple of times that it's like it's hard to get this well defined, right? So in what sense can I even in what sense can I talk about this like the generation time? Because like the trigger event when I have a pure state doesn't really make sense in these systems.
Mm-hmm.
So
wait, why doesn't it make sense?
Well, maybe, or maybe it does make sense, as you mentioned, or maybe the universe was in a pure state before the Big Bang or anything. But if it's not well defined, if I cannot say my dice were in a pure state at this point in time, then how can I properly talk about this generation time in the same sense as I can in the quantum?
Yeah. So the thing is, as you point out correctly, is this generation time in many cases which fall under the term random number generation, it's just not well defined. You can't compute it. But that's part of the argument. So this definition, it was born out of the desire to be able to show that quantum random number generators have an advantage towards classical ones, because there are these people who would like to certify quantum random numbers, and they need a quantity that certifies a quantum random number generator. And so we were like thinking about what kind of quantity can we give them, because they really like to put a number, a stamp on the quantum random number generator. And what they would love to have is that they can like just reproduce the outcome, like deterministically, which doesn't make sense for a random number generator. So we were thinking about what quantity distinguishes quantum from classical ones. And the main point is that for a quantum random number generator, I can actually calculate it. Of course, it doesn't make sense in most classical cases, but the focus was really here to find a quantity that makes sense in the quantum case and somehow shows that the classical case is different. Okay, so now I'm actually almost at the end. So this is like the summary of what I wanted to convey to you, that our definition of randomness is that it's random with respect to some knowledge if the probability distribution is uniform. And it's very important that it's always with respect to a trigger event and not a general property of the randomness. And also that we can define this generation time that allows you to somewhat distinguish between quantum and classical randomness, even if we describe everything quantumly. Okay, and with this, I'd like to thank you for your attention.